right, so today we're going to start building our geometry math, I guess is the best way to say this. Laying sort of the foundation work, getting into some of the basic definitions. Geometry is a very different math than algebra. It has its own vocabulary and set of rules in terms of corollaries and postulates and theorems and stuff. So we have to build all this up. Today we get into a lot of very basic geometric definitions and trying to develop that vocabulary going forward. So we should be able to name and sketch some geometry figures, and we'll talk about points, lines, planes, and the segments, postulates to identify congruent segments. That's the idea behind all of today. Okay. So when we start a new language, which is basically what geometry is, new languages always start with undefined terms. There are things that are there that we will use, that we know we can use, but we just have a hard time defining them. So we can describe them, just not necessarily define them. And those three undefined terms are points, line, and plane. Right? The point is the basic unit of geometry. It has no size. It is only used to show location, right? When we name points, we just use a capital letter. So if I wanted to name these points here, we would just call these guys A, A, and then B, and then C. And we want to separate those with commas, right? Because we don't want to put them all together. We'll use that idea to name other things, right? So just A, B, and C there. And then if we put points together, we start stringing some points together, then we create a line, right? A line is a straight arrangement of points. There are infinitely, I'm going to put all this stuff in here real quick and we'll go through this together. There are infinitely many points on a line, so just because we don't draw a point on a line doesn't mean that points aren't there, right? We just need to identify them, right? So points are no dimension. Right? They do not have, there's no size, right? They do not extend in any direction. They just sit there, right? Well, when we start stringing these points together, we get lines. And lines can extend out in one direction, not one direction, but lines extend out in both directions forever. But it does introduce a dimension. So lines exist in one dimension. If you want to talk about them going in a length, we can do that. Lines don't actually have length, right? Well, I guess they have an infinite length. So we don't actually measure it, but there's no thickness, right? They only go in one direction forever, or two directions. It's kind of tough, depending on how you look at it, how to say that. But anyway, that's a line right here, obviously. I want to make sure that we put arrows on that line so that we know that it will extend in those two directions forever. And there are points even outside of those arrows that are on this line. So this point out here would be on that line as well, right? All right, when you name a line, it takes 2 points to make a line, right? In algebra class, when you're graphing lines, you had to plot 2 points and then draw your line. So it just takes 2 points to determine a line. Therefore, it takes 2 points to name a line. Any 2 points on this line would be okay. So we could call this line DF. But as we're going to find out pretty soon, we're going to name a lot of things with just 2 points. And so we need to make sure that we can tell that we're talking about a line and not anything else. And so we have to use a line symbol above those 2 letters. Now, we can do that. Sometimes there is a lowercase cursive letter sitting next to this line that we can use to name it as well. So we could call this line L. So we could call this line DF or line L. You are welcome to use any 2 letters on this line, any 2 points in this line, like we said before. So we could call it line DE, line FE, line FD. We can go in a lot of different, there are a lot of different options there, or that lowercase l. Okay? So it has an infinite length, but not anything that we can measure, but not a thickness. If we wanted to add a width to that, then we could, and then when we do that, we create a second dimension, and so that creates our planes. Planes have an infinite length and an infinite width, but they do not have a thickness. If you can imagine a sheet of paper with absolutely no thickness whatsoever, that would be your plane, right? Extends, it's a flat surface that extends in two directions forever. So you see that there. Now understand that just because we draw this box does not mean that that is as big as the plane is, right? This point sitting out here could also be in that plane as well, right? It just extends forever. We just got to stop drawing at some point, right? All right, so it takes 2 points to name a line. We need one more point to give us that second dimension. And so we need 3 points to name this plane. So we can name this plane G, H, I. And when we name a plane, it has to be 3 points that are not on the same line. So if you notice, G, H, and I in here are not on the same line, right? If I were to draw a line through G and H, then the I would not be on that line. And it has a lot to do with the fact that you can put, a line can exist in a lot of different planes, right? We'll see that as we go through. So GHI means plane GHI. Sometimes you'll see the actual word plane written in front of it, so plane GHI would work. Or, kind of like a line, we can use a cursive letter, a single cursive letter, to name this plane. When we do that, very often, not very often, we use an uppercase, a capital cursive letter. So this could be plane GHI or W, capital W, and call it plane W. Okay? Those are our building blocks. Those are our undefined terms in which we will use to name, to build the rest of our geometric figures. Okay? All right, some more definitions for you. Collinear. Co means together, means with, means, well, those are the best words to put with as a meaning for co. And then the word line is in linear. So collinear means that things are on the same line. Very often we'll talk about points, but it really could mean anything. Anything could be on the same line and be collinear. So these 3 points are collinear. These 3 are not. And since I mentioned before, it takes 2 points to make a line, any 2 points will always be collinear. If we want to establish collinear or non-collinear, then we have to introduce a third point. So if we ask you for collinear points, you have to give us 3 points. So A, B, and D are collinear here. Or same thing for non-collinear. If we ask for non-collinear points, you have to list 3. You have to list 3 points. 2 points are always collinear. And so that doesn't really help us. It takes 3 to make non-collinear or collinear, right? And coplanar, kind of the same deal. Coplanar means on the same plane. Okay? So these points are coplanar. These points are not. In the first picture, those 4 points are all on that tabletop, so obviously in the same plane. In the next picture, the C has kind of fallen off the table and sits on the ground now. So those are non-coplanar. And kind of along the same lines, it takes 3 points to determine a plane, 3 non-collinear points to determine a plane. So we do require a 4th point to establish coplanar or non-coplanar. And so A, B, C, and D are coplanar in this picture. Or if you want to talk about non-coplanar, A, B, C, and D are non-coplanar here. So you got to make sure you list 4 points. It takes 4 points. Okay, so for collinear we need 3 points. For coplanar we need 4. All right. All right. Some additional. Now, we're going to use the idea of points, lines, and planes to introduce and build more and more geometric figures. Okay? First one we'll talk about is a line segment. So lines have an infinite length. You can't measure it. There's nothing concrete about it. So if we want to talk about concrete, we want to put a measure to something, then what we would do is basically lop off a line, right? So we take a line and we cut the 2 forever ends off, and we create a line segment. A line segment is just 2 endpoints and then all of the collinear points between those 2 endpoints. So this is your line segment. There are still an infinite number of points that are on this line segment in between those 2 endpoints. But the 2 endpoints are important because they tell us where our line segment begins and ends. It tells us where to begin and where to start and stop measuring, right? So since those endpoints are the most important part there of a line segment, when we name a line segment, we would use those endpoints to do that. So we'd have to call this line segment AB. You can't pick any 2 points on the segment that you want. We have to use the beginning and the ending point, okay? But we can't just leave the AB sitting there because, again, we could be talking about line AB, and there is a line AB that exists right there on that segment. We just choose not to acknowledge the forever length. We want to cut that off at A and B. So we do have a line segment symbol, which looks a lot like the line symbol that we draw above the AB, only we don't use arrows, right? Because this guy doesn't go on forever. So that would be line segment AB. There's not a lot of choice here. You could go the other way and call this line segment BA, but those are about your only choices, okay? So that's all about line segments there. Array. Array is kind of a hybrid between a line and a line segment. It's basically us cutting off one end of a line. So array has an endpoint and extends forever in one direction. So these are rays, right? These rays have an end point here and then a directional point that tells us which way the ray could go. Because as you can see, a ray could go this way, or it could go this way, or a ray could go this way, or it could go this way. It doesn't really matter. Rays can go in a lot of different directions. So we need an endpoint and then a directional point to tell us which way the ray is going. Since those are the 2 characteristics that distinguish one ray from another, those are the things that we're going to use to name a ray, right? So we always start with the endpoint first. So we call this ray D, and then the directional point E. And then again, it's 2 letters, so we have to make sure that we differentiate between a ray, a segment, and a line. And so what we do is we use what looks like a ray and draw it above our 2 points. Now, we always want the arrow, there's only one arrow in a ray, we always want that arrow to be above the directional point. So we would want to put it above the E there. Now, it doesn't matter which way the ray goes. We're still going to name it the same way. We always start with the endpoint, then the directional point, and we use the symbol that way. So even if a ray goes like this, we would still start with the endpoint, use the directional point, and then make the ray look like that. We still want to draw left to right. We still want to name left to right. We still want to draw the symbol left to right. Okay? So that's your rays. And just a reminder of what I just said. We always name a ray by the starting point, then the directional point, and then the arrow on top always points to the right. Okay? So that brings us to the idea of opposite rays. Opposite rays are simply rays that go in opposite directions. They share an endpoint and they go in opposite directions. So if I were to draw a ray that went this way, say, and again, we can stick with DE if you want, the opposite ray would share that endpoint and go in opposite directions. So this could be DF. Which means that if you draw opposite rays, it looks a whole lot like just a straight line, right? If we were to name these, then again, we start with the endpoint and the directional point, so ray DE, and then ray DF, the arrow always going to the right. Okay? All right. All right, let's start naming some stuff. Right? So in a diagram, on the left-hand side, examples of points. There are a lot of things that we can just name as points. Obviously, hopefully you see this like E or G or F. We don't want to use M or N. Those are lowercase letters and not how we name points. Okay? Examples of lines. Right? Well, there's a couple of different ways where there are two lines in the picture, right? But a lot of different options for naming those lines. So the first line we could call line EJ with the line symbol. Or we can go lowercase m. The other line we could go HG with the line symbol. Or go lowercase n, right? Either way. Segments. Again, a lot of different options here. We could go JF with the segment symbol, or JG for another segment. There are a lot of different things we could do there. Rays. We could, I'm going to challenge you to find ray FE. I'm going to name it this way. So start at F, go find F, and then go in the E direction, right? There are a lot of different options there as well. Now, can you find other options, right? Other points. Can you list some more points? Can you list some more lines? Can you list some more segments? Can you list some more rays? On the right-hand side, take a second to try to list some more of those. You can stop the video and then start it back up in a second, and I'll try to give you some more examples to see if you come up with the same thing. So, here are those examples that I mentioned to you before. Did you come up with any of those? The difficult part here is you would need someone to take a look to make sure that you've named everything correctly and everything's going in the right direction, all that kind of stuff. So if there are any questions, if you didn't come up with these, if you came up with other line segments rays, just ask me really quick next time you see me to see if you're naming things correctly. All right? All right. The idea behind geometry, I mentioned on day one that geometry is probably the single most applicable math class as far as your core math classes go, between Algebra 1, Algebra 2, and Geometry. But it's only applicable if you can use the world around you, if you can use geometry to model the world around you. So you'd want to be able to draw, really be able to just look around your room right now or whatever and try to figure out what you could let be points, what you could let be lines, what you could let be planes is always a good exercise. The best way to kind of model is to just draw things as well. And so we're going to want to be able to sketch different figures. This is where you artistic people are really going to thrive, and those of you that are more algebra brained are going to struggle a little bit to draw. I have a hard time drawing. There are just some things that you want to keep in mind as you draw these. They don't have to be beautiful pictures, just have to be accurate. And so the first thing, sketch a plane and a line in that plane. What I would tell you is that could look like anything. Here's one example. Just make sure that your line is sitting completely in that box that you use for your plane. Don't let that line protrude out, because if you were to do that, it might start to look a little bit like the next one, which is sketch a plane and a line that intersects the plane. So in the first one, if line AB came outside the box, it might start to appear as though that line goes through the plane and not sit in the plane. So the second one here is an example of a line going through a plane. What's interesting here is if you're ever looking for a point, if you're ever looking for a location, this helps us understand that a line and a plane will intersect at a point. So when you draw this, a couple of things. Number one, you're going to want to label everything. Label your planes and label your lines. And you want to label this intersecting point, right? Show that intersecting point, show where that line intersects that plane, and then make sure you label that. It also helps because we're trying to create three-dimensional pictures on a two-dimensional piece of paper, basically. So if you can imagine that when you draw these things, there are going to be parts of some of our figures that you can't see. And so whatever you can't see, dot it, like right here. This helps us see that this top part of the line is above the plane, and this bottom part of the line is below the plane, because you wouldn't be able to see that part of the line if you were to create that. So we dot that part of the line in. Okay, that'll help in trying to improve the perception of your picture. Okay, and then the next one, sketch a plane and a line that does not intersect the plane. Well, hopefully that's a little bit more obvious. All you got to do is come up with a plane, just draw a box, and then make sure that when you draw your line, it is nowhere inside the box at all. Just kind of let it float above there. Again, making sure that you label the plane, label your line. Okay? Sketch two planes that intersect in a line. So two planes will intersect at a line. Sometimes it's helpful to understand that so that you can find your lines later when you need to. I'm going to take an attempt here at sketching two planes that intersect in a line. It's tough. It is difficult. Okay, so there's one plane, and then I'm going to try to draw another one that is coming out here. You wouldn't be able to see this part of the plane, and then you'd come down here, and then this guy over here. You'd be able to see every part of this, but if you were to do that, you would not be able to see this part of the first plane, so I'm going to erase some of it to try to create that three-dimensional type situation. And planes intersect at a line, so you'd want to include your line here with your arrows and then label them. And so I mentioned before that when you name a plane, you have to use 3 points that are not on the same line. And here's why, right? Because here's a line that sits in two different planes. It sits in plane P, which is the red plane, and it sits in plane, Q, which is the black plane here. Right? Because if those two planes extend out forever, those two planes would capture that same line. So when you name a plane, you need 3 non-collinear points to make sure that you name a unique plane. Okay? But anyway, that's actually not a bad picture. It's one of my better efforts. I'm not usually very good at sketching these pictures, right? But you try to visualize what the diagram would look like and then try to make your diagram look like that. It can be tough. We'll have to practice it some, and you will have to do some sketching on your quizzes and tests, so definitely practice. Okay? All right. That's a little bit more professional looking drawing there. All right? All right. Moving on. We can talk about segments, right? Segments we like to talk about a lot because, like I said before, it's a way to kind of create some concrete figures, be able to measure some things, and come up with some numerical values for your geometric figures, right? So we know that this symbol here stands for a line segment. So if we consider a line segment AB, if we want to talk about the measure, right, the measure of a segment, then we want to put a lowercase m in front, right? Or if we want to talk about the length or the distance from point A to point B, we could just drop all symbols all together and just use AB, right? So you're starting to hopefully understand that symbols are very, very, very important as far as making sure that we understand what figures we're talking about and referencing, right? But whether you write M of A, segment AB or just AB, they're both referring to the numerical measure of a segment, right? All right. So, like I said, we want to measure. We want to measure segments. One way to come up with the length of a segment is to actually use a ruler, right? And so there's something called the ruler postulate. Believe it or not, postulate is just a fancy word for just a rule. There's a rule in geometry that says, the ruler postulate basically says that a segment, the endpoints of a segment, match up to a coordinate. You can make a segment endpoints have coordinates. So like this coordinate would be at 0, this coordinate would be at 5.2, and you can use those coordinates to come up with the length of a segment, right? It's basically what tells us how to use our rulers. So if we are at 0 on the ruler and the other endpoint goes to 5.2, then obviously the measure of AB is 5.2. So we can say that AB is 5.2 centimeters, or we can say the measure of AB is 5.2 centimeters. It means the same thing. Okay? The reason why I bring up the ruler postulate, and I know you guys know how to use a ruler, is that sometimes rulers can get rough edges or they can break or whatever, and you can still use a ruler to measure. We could have actually put the segment here at 1, and then the end point would have been here at 6.2, and still come up with the exact same length. Now your coordinates are 1 and 6.2, and the ruler postulate says to find that length, you would just subtract those two coordinates. So the postulate is kind of what allows us to use any part of the ruler as long as we're subtracting the coordinates. Okay? All right. And I know the ruler is sitting here in the notes. Hopefully you have your supplies that I gave to you in class. If not, grab a ruler, and you would want to measure that segment that's on your notes on your paper. But like I said, I hope that you guys know how to use a ruler, and you would come up with the length of CD here, which is 4.2 centimeters. Okay? All right, so that's using a ruler. Hopefully we're okay there. Now that we can give numerical measures to our segments, then that creates the possibility of being able to add segments together. And being able to add segments together may seem kind of weird if you consider the physical segments themselves, but adding the measures won't be weird at all. So we have what's called the segment addition postulate, which means that if we have two segments that are sharing an endpoint, like that guy and that guy, and they are collinear, right? Those segments need to be collinear on the same line, then we can add those two segments together to create a new segment. So if we add AB, segment AB to segment BC, then physically we would create segment AC. Well, not only can we physically weld those two segments together to create a longer one, we can add their lengths together to create the length of AC as well. So what the segment addition postulate says is that if we take the length of AB plus the length of BC, we should get the length of AC, which I hope seems incredibly obvious, right? But as we start throwing some algebraic expressions in there for our different segments, it's going to be helpful to write out this segment addition postulate just like this. So you label your segment and then write it out. AB plus BC equals AC. And then fill in what you know about those segments, and that will help you figure out what you need to do to find different lengths. Okay? So here's what I mean in the first example. I know that we can just add 380 plus 220 and get to 600 feet. Hopefully that seems incredibly obvious. But what I highly recommend you do is get yourself in the habit of writing out the segment addition postulate, and just using the segments themselves. In other words, I mean, just write out AB plus BC equals AC, and then fill in those numbers. Here it seems trivial to get your 600 feet. But I know it's called the segment addition postulate, but there are possibilities of needing to come up with something like the next example, where you know one of the smaller segments, but you don't know the other one, and you need to come up with it. Well, hopefully it seems obvious again that you're not going to simply add 21 and 36, right? You should see that you're going to have to subtract those. But again, you want to take some of the thought out of it, then just write out the segment addition postulate, fill in what you know, and we don't know BC. And so this equation now tells us that we should subtract 21 from 36 and find our length of BC, which ends up being 15 meters. Don't forget your units. Okay? Now again, in these two examples, it seems very trivial and very easy, but we need to also be able to do this when we put algebraic expressions in there for our segments. Okay? But that's your segment addition postulate, kind of a duh kind of thing, right? All right. Well, as you will find out, geometry exists in two worlds. One where we are just considering the picture, the diagram, the physical geometric figure, right? The other one is where we actually put numerical measures and numbers in there. And when we switch over to that world, our symbols change a little bit and the meaning changes a little bit, right? And here's what I mean. Two segments can have the same length, the same actual numerical length. If they do, then their lengths are equal. Their numbers are equal to each other. And that should make a lot of sense. But if we're talking about the actual segments themselves, then we call them congruent. We use the word congruent. And the congruent symbol looks a lot like the equal symbol, only it has a tilde above it, if you want to call it. That's the Spanish name for that thing. There's a little squiggly line above the equal sign, and that will mean congruent. So, segment AB and segment CD, if we were to measure those two things, they would have the same length. And so we would write out a statement of equality. That's what this is. The length of AB is equal to the length of CD. That is your statement of equality, is equal to, right? Well, if that's the case, then the two segments themselves, not their measures, but the actual segments themselves, are said to be congruent. So segment AB is congruent to segment CD. So we would write it out this way with that equal sign and the tilde above it. In the diagram itself, we would use these tick marks. We use tick marks to show that two segments are congruent. Whichever segments have the same number of tick marks in them, those are the segments that are actually going to be congruent to each other. So here, A, B, and C, D are congruent. Now you can use as many tick marks as you need, because sometimes we'll have multiple sets of segments that are congruent. And so we do use multiple tick marks, right? So we could use 2, or we could use 3. It doesn't really matter, as long as the two segments that are congruent have the same number of tick marks. And you see there, when we start proofwriting, we'll do some proofwriting. When we do, we will use this idea a lot, where if the lengths are equal, then the segments are congruent, and it helps us get a step in our proofs. Okay? So that's just some symbols, some notation there. All right. Comparing segments. Here, we've got two segments on a number line. We've allowed those two endpoints to have coordinates. Like I said, the ruler postulate says that we can subtract those two coordinates and use the absolute value of that difference, right? So the length of AB obviously would be -9 minus -5, and we would make this a plus and get -4, but lengths are never negative, right? Hopefully you'll understand that you can never have a negative length. That's why we take the absolute value of -4 and get +4. CD, same thing. 0 minus 4, which is -4. The absolute value of -4 is 4. So what we see here is that these two segments have the same length, which means that their lengths are equal, but it also says that those segments are congruent. So if we wanted to write that out, like say like this, we would do two things. We could say that AB is equal to CD. That's our statement of equality, which would lead us to say that segment AB is congruent to segment CD. Okay? Now, I'll back up to the number line. Yes, of course, we could just count. We could count from A to B. 1, 2, 3, 4 tick marks means that this is 4. And then 1, 2, 3, 4 tick marks means that this is 4 as well. So we could just count the number line, but I also wanted to use the idea of that ruler postulate to help us come up with the lengths. Okay? But then when we compare those, they're the same. Those two segments are going to be congruent. All right? So there you go. There's a lot of basic stuff that we're going to build a lot of our geometry around. And it's a lot to take in, but come back to the video anytime you need to refresh what we talked about. Okay? Homework sitting out in Canvas. Make sure you get that done by next time.